Hello everyone, I am Dr. Manika Gupta. I am an assistant professor at Department of Geology, University of Delhi. Today in the module, we would be understanding about digital change detection analysis. In this module, you will be able to understand how the satellite images can be used for change detection, what are the various methods we can apply the change detection on the satellite images, and how is the change detection helpful. As an introduction, now what do we imply by change detection? As the term itself suggests, it's a quantitative measurement how much something has changed from at time t1 to at time t2. So basically we are quantitatively measuring some kind of difference which occurred in a region on the Earth's surface which was first understood at time t1 and then we explored it at time t2. Now why is this change detection analysis important? This change detection analysis is important because we need to have some understanding about maybe of the land use land cover change within a decade, or we might want to understand how is the glacier melting, what is the rate of the glacier melting. How can we understand this? We can understand only if we have a temporal change detection analysis. The satellite data here comes useful because we can analyze a larger geographical area in one satellite image which as such is not physically possible. That is the reason that change detection has an important aspect in remote sensing. Once you have classified the images also, then also change detection technique can be utilized. It's also useful in another areas of application like in hydrology. How in hydrology? In hydrology you can have flood mapping, you can have runoff estimation, even a radar data can be used to measure or estimate changes in the discharge data from a certain river. Why are these important? These are important because the discharge data in itself is difficult to measure, especially at high hilly regions. So if we have a satellite data on a temporal scale for such a place, it is easier to measure these changes and provide an estimate maybe for water resource management, for dam construction or anything for that matter. Similarly, we can also have temporal changes measured for suppose as deforestation. So if we have to analyze big forested areas and we want to track the changes in this, easily land cover land use maps converted from the satellite images can be utilized on the temporal scale. So that is the reason this digital change detection analysis have gained a lot of importance. Secondly, it has gained importance because in today's time we have multiple temporal data available from the same sensor. So a continuous availability of the satellite data from the same sensor helps us in recognizing or detecting the changes on a temporal scale. This temporal scale can vary depending on our requirement. It might be daily changes, it might be monthly or even annual or decadal changes. Daily changes could be important if we are monitoring soil moisture. So if we have daily rainfall data, we can easily model or interpret the change detection in soil moisture from the available satellite data. Thus you can see there are wide applications when you have a multiple data set and you can employ this change detection technique. Now before we understand what are the different approaches for this change detection analysis, you need to understand while applying change detection there are few criteria which should be met and you should remember these before performing a change detection analysis. Now what are these criteria? First, when you are performing a change detection, the two satellite images which you have should actually be at the same spectral, spatial and radiometric resolution. If you are comparing a 2-bit image with an 8-bit image, you will have lot of detections in the changes and you might say, oh, this is a great change in the image. But actually that might be due to a difference in radiometric resolution and it might not actually show the change in the region there. So it is important before you perform a change detection analysis, you actually know the satellite image resolution. The second resolution I talked about is your spatial resolution. Spatial resolution for a MODIS might be 1 kilometer and for a Landsat would be 30 meters. So if you subtract one image from the other, you will get a lot of changes again. But this would not be again a justified change detection because the spatial resolution is different. So the per pixel resolution in change detection should be same. That is, your spatial resolution should be same before you undergo this change detection analysis technique. Third is your temporal resolution. Now temporal resolution, suppose you have a classified image as you did in your supervised classification or unsupervised classification. Suppose you classify an image of a region in January and your second image is classified in April. So if you create a change detection map from these two images, you will notice there can be a lot of differences. Why? Especially if you are treating the area where there is a lot of crop or agricultural area, there is going to be a lot of difference as such because of the phenology of the crops that have been planted there. So that is only a seasonal variation. It's not a major change or it is not a major detection to be done. Major detection changes implies that in a year or so, suppose the water level has gone down. So that is your change detection. Here you will have to mention these are seasonal changes where the crop tile changed in January from in April. So these are not permanent changes but temporary changes. So if you want to notice only temporary changes, then you can have the change detection technique in January to March. Otherwise, if you want to notice the permanent changes, which is the major task for change detection, then you need to remember that both the satellite images for which you are considering the change detection have to be for the same time. Next is your spectral resolution. Your spectral resolution is again the same thing. Like if you have a Landsat data, that's your multispectral data and the other is your hyperspectral image. So if you are comparing a spectral data image of the Landsat with the hyperspectral image, obviously there is going to be difference. Why? Landsat bands represent discontinuous bands while the hyperspectral has multiple bands in the same band zone in which a single band in Landsat is representing. So because of difference in the spectral resolution in the bands, if again you do a change detection, there are going to be issues and it will not be showing you exactly the significant changes which have occurred over time in the analysis. So these are the basic criteria which you need to remember before you go for a change detection analysis. Another approach is which you need to remember is the images need to be georectified before you perform an analysis over them. Georectified implies that the same pixel should be at the same spatial location for both the images. If there is an error during georeferencing of either of the tiles or either of the satellite images, they would not superimpose upon each other. So before you go for change detection, you need to superimpose the both images and see whether they are overlying upon each other or not. If they are not overlying upon each other, you need to take care of it before you can perform this change detection analysis. Now the most foremost analysis technique is visual interpretation. What implies by visual interpretation? Suppose you have the band composite or the false color composite of the same area for 2 years, you can visually identify the changes which is occurring in reflectances in the two images. Now even in visual interpretation, you need to realize that the two images should be orthorectified. They should be rectified for atmospheric corrections and they should be located at the exactly same period of time. So you can visually see the difference in the spectral characteristics because the change in spectral characteristics can be shown in the softwares through the change of the tone in colors. A bright red color in the NIR region might reflect a healthy vegetation, while a little lighter color in the same time period might represent a bit non-healthy vegetation. That is how you can see the pixel changes. However, in visual interpretation, you are not exactly quantifying the changes because you are just visually saying, okay, there is a certain change. But how much area is changing? What is the rate of the change? What is the trajectory of the change is not clearly obtainable through visual interpretation. So therefore, we need some kind of digital techniques where can we analyze this quantitatively. So in quantitative analysis of change detection, the first technique, and which is the foremost technique that is used, is the algebraic methods. Now in algebraic methods, as the name suggests, you can understand we use certain mathematical operations on the images that could be like maybe subtraction or division. Now how does the subtraction works? Subtraction is, suppose you have two images and you have the NIR bands of both the images. Now if you take the NIR bands of both the images, you just subtract one NIR band at time t1 from the NIR band at t2. Once you subtract, you will get certain results. Now these would be pixel by pixel changes. So at each pixel you can notice a value of 0 or a higher positive or a negative value. So here a value of 0 would obviously represent no change, while a value of negative or a positive represents a increase or decrease in the digital number value in the NIR region. So this is one of the basic things which we can apply to any of the bands as per your requirement. I gave you an example of NIR because you can easily notice the most reflection for the vegetation is in NIR region. So we consider this band number 4 of the Landsat 7 data. But if you are looking for the coastal data, maybe the blue band is better. So you can look for the changes during using this method in band 1 also. Once you have done this, the drawback is you cannot actually realize the increase, the meaning of the increase and decrease in the NIR values exactly at the aerial time, because it's for the one satellite band, and these might change based on other bands also. So it helps in the starting analysis, but you need to have some other method also to decide what is the threshold changing. If it's becoming negative, then what is the threshold value which implies a significant change. So instead of using only a subtraction method, there are other methods like band ratioing. Band ratioing implies that you have a ratio of NIR band of 1 with NIR band of the second image. This ratioing also tells you the similar thing as the subtraction method. The third method here could be used with the indexes. Now for an example, you have NDVI. What is NDVI? NDVI is Normalized Difference Vegetation Index. In a single image, NDVI is calculated by a ratio of NIR value of minus NIR upon NIR plus R. So you can have this NDVI value at time t1 from satellite image 1 and at time t2 from satellite image 2. So your NDVI value implies the health of vegetation at any particular time. This value varies because it's a normalization, so it varies between -1 to 1. So if it's a -1 value, there is no vegetation, and 1 represents a very high value of vegetation or a healthy vegetation. So you can see this is your NDVI value. Once you have it at T1 and T2, you can just simply subtract from the raster pixels. So if you have this two NDVI values each at T1 and T2, suppose this is 0, 1, -1, and this is 1, 0, this is again 1. So when you are subtracting these two images, you get a third image which would be, so if you have this 0, -1, this would represent -1 here, and this is 1, so this will remain 1, -1, 1, this is 0. So you see with time there is a change in the values here. So what was in the first time as vegetation, it reduced here in the time T2, and it again in a change detection you will see that there is a difference, and it's again here 1. So you can notice there has been a change at this pixel in the vegetation. Similarly at this pixel also, even though the first time there was no vegetation, even though there is a vegetation and a negative sign implies that if from non-vegetation pixel it has changed to a vegetative pixel. So this is another method where you can identify based on the band ratioing after the normalization of two bands. So instead of using only one band data, here we utilized two band data. Other indexes are also available and you can apply the similar approach on any of the indexes available to you. Only the process will be the same as suggested here. Other than the band ratioing and subtraction, we can also utilize regression analysis. Now we can create a regression equation between the band data of the two time periods, and based on the regression equation we can find the difference in the two images. The fourth one is your mean vector analysis. Now the subtraction or the band ratioing were based on only one band data from each of the images. Suppose you want to work on multiple band data, then you can use a mean vector analysis. In mean vector analysis, for an example, I will be showing in a simple way using only two bands. Suppose in NIR band at T1 and at T2, we have a value of 100 here and maybe 60 here, and in NIR here we have 24 and here we have 30. So these are two bands here for one pixel. Now in space, feature space, if we want to plot these, so we have NIR here and NIR here, we have 2 points. So NIR is representing from 0 to 40, suppose 10, 20, 30, and this is suppose 100 here. So you have 100 is here and 24 would be around somewhere here. This is your one vector here, and this second vector would be around somewhere 60 and 30. So it would be somewhere here. So this is the pixel value for the same vector, but what is happening here? The values have changed between T1 and T2 in both of the vens. So this is your vector here. Now we can calculate the change in magnitude based on the Euclidean distance. For calculating Euclidean distance, we have simple formula here, where what we do, we calculate the distance between the points in the NIR region and the R region. So here we get 100 minus 60 whole square plus 24 minus 30 whole square. So that is the magnitude of change in feature space where we have two bands. Similarly, if we had 3 bands or 4 bands, we would add those values to this same. Now this only gave us the magnitude of change at that particular pixel. How about if we also want to know what is the direction of that change? Implies if it's towards T1, if it's reducing in T2, or if it's increasing. So we provide an angle for this calculation and it tells the direction of the change in vector magnitude. Suppose you also want to know the change in direction for these two bands. So what do? We provide a formula, we use a formula where alpha is equal to cos inverse dot product of x1 and x2 upon x1 plus x2. So here the dot product of x1 and x2 will be represented by matrix multiplication of this and this. So this represents the upper portion, and your x1 is actually the value of this length. How do you calculate this value? It's a simple Pythagoras theorem. So for this value you would have the value for x1, suppose this represented your x1 and this was your x2. So for x1 it is equal to square root of 100 square plus this value is 24 square, and for x2 the value is square root of 60 square plus 30 square. So the calculation of this gives you an alpha angle which is represented here. So you get the direction of the change in magnitude which happened during from T1 to T2. So this was your change in vector analysis or the mean vector analysis method. Another methods which can be applied on the images directly are the transformation methods like PCA or the principal component analysis. Now in principal component analysis, it considers multiple band data and it transforms them orthogonally so that you can have the highest variance available in least amount of data. That is, it reduces the redundant data from the 6 bands. It is assumed when a spectra is representing one pixel in the 6 bands, there is some correlation in those values between the bands, so as to have the maximum variance in the data and minimize that data from 6 bands to at least either 2 or 3 bands. We perform principal component analysis, and the bands we get are known as principal components. Now, once we have performed the principal component analysis for the images of T1 and T2, we can simply use the algebraic options and have a differencing map or the ratio map similar to the algebra option. However, this method is better than using a simple method because it already had a maximum variance data available, and it is able to show or detect the changes much more easily. So, these were your algebraic change detection analysis methods, and these are also known as pre-classification technique changes. Why were these known as pre-classification technique changes? These are the pre-classification technique changes because we had not performed any kind of changes on the images, or we were having the requirement of change detection only on the basis of spectral characteristics. We did not convert these information into any kind of informational classes here. So, to find an information about the change in informational classes, what are the informational classes? We already studied in the previous modules. So, to understand the changes in information modules, we need to classify these images first. So, these techniques were pre-classification technique change detection methods. Now, we will talk about post-classification change technique detection methods. Now, post-classification technique changes implies we already have converted our satellite images into either supervised classification method image or an unsupervised classification technique method image. So, these images can then be utilized for change detection. Now, what happens? Once you have a classified image from T1 and one classified image from T2, you can easily again do the subtraction method in these two images, but now you will get an image which tells you whether the pixel has changed from an urban land to a water body or from an agricultural site to an urban area. So, suppose you had 3 initial classes of agriculture, urban, and maybe something else like forested area, and in time T2 also you have the same 3 classes. So, if you subtract one image from the other, you can easily quantify how much of the urban area was increased from time T1 to T2 in the second image, and how much of the forested area was thinned or reduced because of the expansion of the urban area. Now, if you have a pixel based image, you will get this change information pixel by pixel. Now, in this image, if you suppose only want to detect the changes in the urban class, how can you do this? So, at T1 suppose we have an image here, and it is again a raster, and same is the image at T2, which is also a raster image. So, in first classified image, suppose this was urban, but this was forested area, and this was urban, and these were other classes. Similarly, in T2, now this remains urban, but this becomes urban here, and this also urban, and this was urban, so it converts to maybe agriculture. So, you will see from time T1 to T2, we have a change in information class with a classification technique. So, you can identify how much of the area from forested was converted to urban, and if urban was converted to agricultural area. So, whatever classes are being considered here, for each of the classes we can have a matrix which suggests which class got converted into which class and how many areal change was there within the time period of T1 to T2. This study is highly equivalent or highly useful when you are studying about urbanization, or you are studying about how the forests are being eliminated in the area on a decadal period. So, every 10-year image can be utilized to do this. However, to perform this kind of analysis in post-classification techniques, you need to remember that first of all, both the images classified should be classified using the same method, so as the amount of error present in both the images is nearly equivalent. Both the images classified should be of the same time period in the year being considered. So, this image change detection should be only for either December images at T1 and T2 or any other month, but it should be the same time period. Secondly, their spatial resolution should be same. You cannot have different resolutions. Plus, if you are using a supervised image classification, then you remember that the training sites have to be calculated or considered during the same time period when you are having the classification done. So, if you are identifying the changes in two time periods, then you should already have the reference sites, your training sites for both the data separately. You cannot use the same training site for both the images. Thirdly, post-classification technique is better from the pre-classification techniques because the errors due to atmospheric corrections have been overcome in these classification techniques. So, these are less prone to atmospheric issues if you have already classified the images and are based on your information classes. So, this was your post-classification technique. Once you have detected these images based on the subtraction, you can also employ other kinds of techniques here, like the pixel neighborhood basis. So, in pixel neighborhood basis changes, you can do it on the objects also. So, in the pixel neighborhood analysis, you can easily identify the association of the pixels together and you can have those change detection quantitatively measured. Another approach could be for the object oriented one also, where you can analyze the segments which occur in the both classified images. So, after classification also this change detection technique is an important technique because you are now able to identify the changes which is occurring in the land use land cover of the region or of the globe also. So, you can perform these change analysis in today's time for the whole globe at one place, and you can understand how the scenarios are changing at monthly, annually or decadal times. Now, after the post classification techniques, we can also utilize it in GIS. In GIS, how can the change detection be helpful? In GIS, we usually use it for maybe overlaying maps or hydrological analysis or deriving some vulnerability maps. So, when you are deriving some vulnerability maps, you usually utilize the land use land cover changes. So, if you have the land use land cover maps from two time periods, you can have the vulnerability maps developed at both the time periods and you can see or make a decision how the scenario has changed. So, if flood mapping has to be done and urbanization has increased in the flood zone, so you will realize that the warning to be provided has to be more immediate as compared to when it was during earlier years. So, therefore, in GIS also you can have changes known for the derived maps. That is why this change detection technique can be very useful. I just gave you an example of one flood mapping, but there are other uses also in GIS where you can use this change detection technique. So, in the end you will notice that there are a lot of uses of the change detection techniques. However, there are certain limitations and you need to take care of these limitations before you provide any details about the significant changes occurring in the images over time period. That is what I will repeat again. You need to remember about the atmospheric corrections, you need to remember about the spatial resolutions, you need to remember about the spectral characteristics of both the images. Then only you can justifiably say that the images have been correctly identified and the images have given you a correct change detection theme for the particular region or particular area. So, other than the multispectral images, you can do similar analysis on the radar data also. How? A radar data actually calculates sometimes it is used for calculation of suppose a discharge data. Now radar data calculates your altimetry or the change in height. So if the discharge is changing, you will notice a change in height data within time t1 and t2. So the radar data can also be utilized for change detection techniques, and it's really helpful when you can have it at large temporal scale for measurements like discharge. There are other uses also even for the radar data. So whatever satellite data is there, in summary, if you have a temporal data available to you, it can be easily utilized for change detecting, which helps you in making spatial decisions for the area at the regional level or at the even global level. Because of these change detection scenarios, we have been able to look at the glacier melting to know that what was present 10 years or 20 years back and what is the situation today. Even for the CO2 levels or the aerosol levels in the atmosphere, the studies have been possible because of multi-temporal analysis, and we have been able to look at the situation on the global level and not only at one city or one state level. This study tells you that how this change detection technique is actually being implemented in every area and what is the usage of this technique. So this was the end of it, and there are books which have been provided as a reference for this module, and I hope you will be able to read them and understand. And you will notice that there are certain more methods for change detection techniques, and you can clearly and easily, I hope, understand from the references. Thank you.